In this presentation I'm going to explain how the Z-transform equation works, with particular focus on why it's used for analysing systems. Check out the description part of the video for links to code and other relevant material, and please subscribe if you'd like to be kept up to date with this channel. The unilateral version of the Z-transform is given by this expression, and you can see that a signal x of n is being multiplied by another signal z to the power of minus n, where the variable n represents the sample number. Basically, this mathematical process is used to identify the presence of exponentially increasing or decreasing oscillations in the signal x of n. I'll explain how this is achieved later on by explaining in detail what z to the power of minus n is, but let's start by understanding why it's useful to identify the presence of these exponentially increasing or decreasing oscillations in a signal in the first place. The Z-transform becomes really useful in the analysis of systems, and it's very often used to analyse the impulse response of a system. The reason for this is because the impulse response of systems with feedback contain oscillations that increase or decrease over time. This is quite obvious in these examples, where it can be seen that the oscillations are decreasing over time. Systems that oscillate in this manner are said to be stable. If the system coefficients are changed, then the impulse response also changes, and we can see that in these examples the oscillations are increasing over time and are therefore unstable systems, which are generally undesirable, as the outputs of such systems will quickly fall outside the linear operating range of systems and start to behave a bit unpredictably. So one of the main reasons for using the Z-transform is to identify whether systems are unstable or stable. For the sake of completeness, I should mention that the Z-transform can also be used to identify the presence of signals that increase or decrease over time but don't oscillate, or if you'd prefer, that oscillate at a rate of 0 Hz, like the ones shown. Another useful property of the Z-transform relates to its ability to determine the frequency response of a system, as well as its use in helping to design a system to have a particular frequency response. As you probably already know, systems frequency response basically tells you how the amplitude and phase of sinusoidal signals will be altered by a system. By examining a system's magnitude and phase response plots, we could find out how any sinusoidal waveform would be altered. This is of course very useful, since any signal can be decomposed into a set of sinusoidal components. Now, one way to determine the frequency response of a system is to pass an impulse through it, since an impulse is a signal that contains all possible sinusoidal frequency components. If you then perform a Fourier analysis on the impulse response, you'll be able to see how every sinusoidal frequency component was modified. I'll provide a link in the description part of this video if you want a more detailed explanation of this. So the key points I'd like to make is that by identifying the presence of increasing or decreasing oscillations in the impulse response of a system, we can determine if that system is stable. And secondly, by identifying the presence of sinusoids in the impulse response of a system, we can determine the system's frequency response. Now, by applying the Z-transform to a system's impulse response, we are performing both of these tasks. And now what we're going to do is take a closer look at how it does this at a mathematical level. As you can see in the equation, a signal x of n is being multiplied by another signal z to the power of minus n, where the variable n represents a sample number. Let's illustrate this process using a very basic signal x of n, which is just 4 non-zero values, and it really doesn't matter what these values are. Now, the Z-transform is evaluated for different values of z, but let's take a closer look at a really simple case where z equals 1. Then the signal z to the power of minus n is just a sequence of ones, which is a non-oscillating or DC signal. After multiplying the two signals, a new signal will be produced, and the samples of this new signal are then summed to give a numerical result. Now, this process of multiplying signals and summing the samples produced is known as correlation, and it's a very well established technique used to compare the similarity between two signals or to identify the presence of one signal in another one. In general, the larger the magnitude of the numerical result obtained after summing, the more strongly present one signal is in another one. In this example, the correlation result of 2 tells us that there's a non-oscillating or DC component present in the signal x of n. If we were to look at a second example where x of n was equal to the sequence 3, minus 3, 3, minus 3, then the correlation with the signal z to the power of minus n, when z is equal to 1, would be 0, indicating that there was no DC component present in the signal. So we've taken a look at how the Z transform works for a very simple case where Z is equal to 1. Now let's look at how the Z transform works in a more general sense. And in order to do that, we have to get a better understanding of what the signal Z to the power of minus n represents. Now, what we're going to see is that Z to the power of minus n can represent any of the signals being shown depending on what the value of Z is. So the Z transform is basically just a correlation or a measure of similarity with all of these types of signal. What I'd like to do now is to try and get a better understanding of how the choice of the value of Z influences the signal Z to the power of minus n. Now the variable Z is basically just a complex number, which is normally represented in this form where or is just a real number and it's been multiplied by e to the power of j omega, where we'll see that omega is used to represent angular frequency in radians per sample. What's really important for us is to be able to visualize the signal Z to the power of minus n, since this is the signal x of n is being compared against using the correlation approach. The signal Z to the power of minus n is made up of two parts, or to the power of minus n and e to the power of minus j omega n. We'll start by examining or to the power of minus n, and if you plotted or to the power of minus n against n, you'll see that it's an exponentially increasing or decreasing curve depending on the value of or. When or is greater than 1, the curve decreases. When or is less than 1, the curve increases, and when or is 1, there is neither an increase or a decrease, and or to the power of minus n is a constant value of 1. For those who are more used to exponential curves being shown in the form e to the power of minus sigma n, you can replace or with e to the power of sigma, where sigma is set equal to the natural log of or. The e to the power of minus j omega n part of the signal Z to the power of minus n can be broken down into cos omega n minus j sine omega n using Euler's formula, and can therefore be visualized as a pair of sinusoidally oscillating components, a cosine waveform and a sine waveform, with a frequency of omega radians per sample. Since the signal Z to the power of minus n is the product of or to the power of minus n and e to the power of minus j omega n, then Z to the power of minus n can be visualized as a set of oscillating components which are generally increasing or decreasing exponentially over time, except when or equals 1. It's important to remember that Z is just a complex number, which can also be represented in the Cartesian form a plus jb, and that or is the magnitude or modulus of Z, which is equal to the square root of a squared plus b squared, and omega is the argument or phase of a plus jb, which is equal to the inverse tan of minus b over a. To get comfortable with the Z transform, it's very useful to be able to visualize the signal Z to the power of minus n for different values of Z. To do this, let's plot the signal Z to the power of minus n for different values of Z and show where Z will be positioned on the Argand diagram. The Argand diagram that I'm showing now has a unit circle superimposed on it, which has its centre at the origin and goes through the points 1, j, -1 and -j, which are shown as red dots. Any point on the unit circle is associated with a complex number which has a magnitude of 1. This means that if Z is located on the unit circle, the signal Z to the power of minus n is comprised of two sinusoidal components which don't change in amplitude. If Z is set equal to j, then the sinusoids will oscillate at pi over 2 radians per sample, since the argument of 0 plus j is pi over 2. You can see in the plot that there are 4 samples per cycle of the sinusoids, which makes sense since there are 2 pi radians in a complete cycle, and the frequency of the sinusoid is pi over 2 radians per sample. This also means that the period is 4t, where t is the sampling interval, and the frequency of the sinusoids can therefore also be expressed as fs over 4 Hz, where fs is the sampling frequency in Hz. Now let's take a look at a few more examples of how the signal Z to the power of minus n would be influenced by the choice of Z, the value of which is shown as a green dot on the Argand diagram. If Z was chosen such that it moved clockwise around the unit circle, then its associated signal Z to the power of minus n will decrease in frequency until it reaches 0 Hz. When z is equal to 1 plus 0j, the argument of z is 0, which implies that the signal z to the power of minus n doesn't oscillate, and since r equals 1, the signal z to the power of minus n is just a constant sequence of 1s, and you'll notice that its imaginary terms are 0. If z lies on the real axis of the Argand diagram, the signal z to the power of minus n won't oscillate, but will increase exponentially over time if it lies between 0 and 1, and will decrease if it's greater than 1. You'll note that the scale of the vertical axis has now been changed, and that I'm not showing the exact amplitude values any longer. If z lies outside the unit circle and was to move counterclockwise, then you'll notice that the frequency of oscillation increases, and we'll get the reintroduction of non-zero imaginary terms in the signal z to the power of minus n. If z was then to move along a straight line back to the origin, then you'll notice that the frequency of oscillation doesn't change, but the rate at which the amplitude of the signal z to the power of minus n increases or decreases is then dependent upon its distance from the unit circle. An interesting thing happens if z was to continue to move along the unit circle in a counterclockwise direction past the point minus 1 minus 0j. It can be seen that the frequency of oscillation of the signal z to the power of minus n starts to decrease, and the phase of the sine wave component is inverted. The reason for this can be understood as an aliasing phenomenon from a signal's perspective, or for those mathematically inclined, from these trig identities. If z was to continue to rotate counterclockwise around the unit circle, the frequency of oscillation of the signal z to the power of minus n would continue to decrease until it reached the position 1 plus 0j. Once this position was passed, the frequency of oscillation would then start to increase again. Why this happens can once again be appreciated by taking a look at the following trig identities.